This is a quick video to demonstrate to you how we might derive one of the kinematics equations. And I show you this because I want you to understand that these equations are not magic. They don't come out of nowhere. They're based on logical principles. And the principles that we're going to base this on is the idea that if we know two things that are true in physics, we can combine those two things together to make a third thing that will also be true. So here's the first thing that we know to be true, is that acceleration is the change in velocity over the change in time, which often we actually write more like this. Acceleration is Vf, the final velocity, subtract off the initial velocity over the change in time. And this would be something you would experience on a daily basis. So imagine you're driving on the highway and you have to pass somebody and you accelerate from 100 kilometers per hour up to 120 kilometers per hour in 5 seconds. So the acceleration rate would be that final velocity, which is 120, subtract off the initial velocity, which was 100, okay? So that's the first thing that we know to be true. So what I'll do is I'll just move this up here, put that out of the way. The second thing that we know to be true is pertaining to when we were working with graphs, okay? So what we need to remember is that on a velocity time graph, this is what it would look like for an object that was accelerating from a specific velocity, initial velocity, up to some final velocity, okay? So over the course of time, the velocity has changed from this amount, so we'll call that the v initial, up to this amount, so we'll call that the v final, okay? And what you may remember from yesterday's lessons is that the area beneath a velocity time graph, so this area in here, if you can calculate that area, then that area is equal to the displacement of the object, okay? So let's have a closer look at that on a new slide. Okay, so the first thing that I want you to notice here is that the area beneath this line that fills up this space down here, so let me sort of section it off here. So this area actually is sort of composed of two separate shapes. We have what looks like a rectangle here and what looks like a triangle up here. And so if that were the case, then area is actually pretty easy for us to calculate. So let's put that off to the side. We know from basic math that area, the total area is going to be the area of the triangle plus the area of the rectangle. And we know the area of the triangle is 1/2 base times height. And we know the area of the rectangle is length times width. Okay, so once again, let's put that off to the side so we don't forget. Okay, so the thing is, in math we call them base and height and length and width, but we don't actually have to use these values. Those are just placeholders. We actually have values and variables that we would use in physics. So if I was going to rewrite this equation with using our variables from the graph, I see that the base of the triangle, well, that's right here, and that just is the amount of time that this thing was traveling for. That's the delta t. So I'm going to instead write the area of the triangle as 1/2 delta t, and I know that the height of the triangle goes from here, which is vi, up to here, which is vf. So the height of the triangle is going to be vf subtract vi, okay? And all of that, the height of the triangle, we have to add to the area of the rectangle. So once again, the length of the rectangle we see is delta t, and the height of the width of the rectangle, it takes us up to vi, okay? So I'm going to rewrite this a little nicer. We know that area is displacement, so instead of writing area total, I'm going to write displacement total, and that's going to be equal to 1/2 vf subtract vi delta t plus vi delta t. Okay, let's put a box around that. What I hope you'll notice is that there are some rearranging that we could do here. So for example, if I was to expand these brackets, I would notice that I had a term with a vi and a delta t, and over here I have a vi and a delta t. So I'm not going to go through all the math, but what I'm going to do is show you what the product would be if I rearranged all of this equation, combined the like terms to come up with a rearranged version. So if we rearrange the equation from the previous slide, then what we end up with is something that looks like this. Displacement is equal to Vi plus Vf divided by 2 multiplied by time. Okay, once again, I'm not going through the explanation of how I rearrange that. If that's something you wanted to do, then I would encourage you, if you like math, go ahead, play with those equations. It's fairly simple arithmetic and algebra, but I'm not showing that right now. So if you'll recall, what we're trying to do here is combine two things that we know to be true. So the first one from the very first slide was the idea that acceleration gives us this formula. Okay, so that was number one. And number two, what we just figured out is that displacement is equal to this equation. Now, like I mentioned, what we want to try and do is combine these two equations to produce something that is new and also true. So let's do that first of all by rearranging this equation at the bottom here. So I'm going to take this one, and instead of writing it as A is VF minus VI over delta T, I'm going to write it as, rearrange it so that I have VF is equal to VI plus A delta T. And once again, I'll leave you to play around with rearranging equations on your own. But what you can see here is that if this is true, if final velocity is equal to initial velocity plus acceleration times time, and this is true, then really there's no reason why I can't take this equation, that's true, substitute it in for VF, and rearrange to create a new equation. So let me show you what that would look like. So then substituting this formula, the second formula into the first formula, I'm going to have displacement is equal to initial velocity, which is right up here. Then I'm going to say plus, but instead of writing the VF, what I want to instead write is this expression, VI plus A delta T. That's all divided by 2, and we know that we're multiplied by time. So we can try and simplify this expression a little bit. We have a VI and a VI, so we can add those two together. It's divided by 2, and we have a delta T that's outside the brackets, and maybe we want to multiply it in. So typically, once this equation is rearranged, it almost always ends up looking a little bit different. I'm going to show you. It looks a little bit how we usually write it in physics. Displacement is VI delta T plus 1/2 A delta T squared. Okay, and once again, I'll leave you to rearrange that on your own, but what you can see here is we have a new equation. This is unlike anything we've seen before, and what's especially interesting about this equation is we do not have a final velocity, right? So this equation shows us we have a D, a VI, a T, and an A. So if you were solving a problem and you didn't know anything about the final velocity of the object, then this would be a great equation to use. If, by contrast, you happen to know, for example, in this equation, we know T, A, VI, and VF. So this is a useful equation if, in the question, you know nothing about the displacement. Okay, so the D is not in that equation. So if you didn't know anything about the displacement, that's not going to stop you from solving other things because it's not a part of that equation. And over here, we have a displacement, initial velocity, a final velocity, and a time. So this equation becomes useful in situations where you don't know anything about the acceleration of the object. So you see here, we're creating these scenarios that will become useful. They are tools in our toolbox. From time to time, in different questions, you're going to have to choose which equation is most appropriate for that scenario, given the variables you know and the variables you don't know. So all in all, we have so far created 3 equations. We know the first equation is the acceleration equation. The second equation came from the motion on the graph. We now have a third equation. But physicists have gone through and actually done this process a number of times and have been able to create 2 more equations. So I'm going to show you. So the final 2 equations can be discovered in a very similar sort of way, and I'm just going to tell you what they are. The first one is that displacement is equal to final velocity times time, subtract 1/2 of acceleration times time squared. And I know you might be thinking that looks like the other one on the other page, except notice that this one uses final velocity, and it has a negative sign instead of a positive sign. So that's different than the one on the last page, which used initial velocity and a positive sign. And the very last equation to show you is this one, final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. Okay? So all in all, we have 5 equations, and each of those equations is useful because it eliminates one of these 5 variables. D, A, VF, VI, and delta T. And with those 5 equations, you can select which one to use in a particular question based on what information you have and what information you don't have.